So far we have used derivatives of functions to approximate functions by simpler functions. Namely, we had seen in a particular theorem whose number I haven't at hand, I don't have at hand, but we have seen that previously we have used derivatives to approximate functions and functions which might be very complicated, and we have approximated them by linear functions. So we have derivatives as slopes of tangent lines of a graph, and the tangent line is an affine linear function, so some linear function plus some constant. So to approximate functions by affine linear functions, which means polynomials of degree 1. Of degree 1. Okay, so this is what we've done so far. The idea is now to use the higher derivatives to approximate them by slightly more complicated functions. Namely, so now the idea that we are going to follow in the rest of the section and also in the next section is that we want to use higher order derivatives to, of course, locally approximate. That was always the idea, to do this locally. Approximate functions by polynomials of higher degree. By polynomials of higher degree. Okay, why is this useful? Similar as to the situation with local approximation by linear functions, the idea is really to have very complicated functions, or functions we don't fully understand, but to approximate them by functions that we can use. Remember polynomials? I've argued in an earlier video that these are really also good for computers, for computer algebra systems and so on, because polynomials, they consist of multiplication and addition, always and always. And this is things that a computer is can do very well. So we can, if you have a polynomial, we can feed this into a computer and do computations, which we might not do with a very, very complicated function that somehow pops up in our physical situation or whatever. So if we have some physical model, which is a very complicated function, locally take the polynomials and let the computer do its job. So polynomials are always really good because they are really the most elementary functions in that they only require addition, multiplication, nothing else. So these are always very good to handle. So why might this be interesting to consider these functions of polynomials of higher degree? Let me just draw some simple example. So assume we have some function, I don't know, which behaves quite wildly. Whoops. Whatever. So assume we want to approximate it at the point. So let's assume we are, let's take this here. So this is the point A. So in this situation, if we would approximate this function by a linear function, this would mean we would kind of enter the tangent line here. The tangent line would be something like this. Okay, this would be the tangent line to the graph. And we see that locally, this is very close to the graph. But we see if we go further away, the difference between this function and the graph becomes quite big, quite fast. And we see that kind of as soon as we go a bit to the right here, this doesn't tell us anything about the graph. So it's really only telling us in this very local situation. So now, if we would approximate this by a polynomial in degree 2. A polynomial in degree 2 is a quadratic function whose graph is a parabola. So we can approximate this by a parabola. So we might take a parabola which looks somehow like this. Okay, so here we again see this approximates the function. Oh, maybe it should be flatter in here. Okay, sorry. Something like this. So assume this is a parabola. And here we can already see that this does a much better job at approximating, because here we see that here if we go to the right, this kind of a parabola which has this slope in here, we can just get a grasp of the behavior of the graph a bit better than before. Now, if we would have a polynomial of degree 3, and we would approximate this by the graph of a polynomial of degree 3, a cubic function, there we know that this can take one more bend. So here we know that this is always a parabola, but for a degree 3, we could have something which goes up to a maximum, then down, and then up. Or the mirror image of this, as the same as the parabola, could be kind of flipped. But here we could then take a function in degree 3, which would maybe look like this. We would go from here, go through here, that take that bend, and here we would have something like of degree 3. And we can see that kind of this always becomes, yeah, of course I should take this, sorry, this is not very wisely drawn. Let me take it like this. So assume we have some, so that here, and here we see that kind of this is still more appropriate to the actual behavior of the function, because here we can see that this goes here and there and there. And so this bend here is then covered by this degree 3 curve as well. So if we go to degree 4, we could do even more, and so on and so on. So the higher the degree of the polynomial, the more bends and turns and twists we can model. So higher degree is usually better to approximate this function, because if you really compare now this pink curve with the original line here, that's a really big difference. I mean, this line doesn't tell us, yeah, not much about the graph, but this pink one is much better. So this is the idea here. These higher degree polynomials might be much better at approximating, really approximating functions actually. And this is what we want to show, or what we want to discuss. So what's the idea? The idea is we have some, assume we have some function going from some interval to the complex numbers, and assume this is n times differentiable for some n. And we want to approximate this by a polynomial of degree n. Okay, so n is some natural number, and assume we have some position, some point a and I, where we want to locally approximate this. So what we want to do is we want to find a degree n polynomial which I call Pn, which is, of course, polynomials are always defined on the whole real line, going to the complex numbers. And I want to write this in a certain form, which I will, let me leave this out for a second. What I want now is to have this polynomial coincide as good as possible, and this means we do not only want f to coincide with the polynomial, but we want the derivatives to coincide as well. This means we want that the kth derivative of f in A is the same as the kth derivative of Pn in A, and this for all derivatives, for all 0, 1 to n. Remember that for k equal to 0, this just says that f and the polynomial, that the values of the functions coincide. So the values of the function and the value of the derivatives should coincide to degree n. This is our idea of approximating, and we will now later see that this really does the job of approximating the function as good as we can. But this is the main idea, to have the same slopes and the same situations here. So a polynomial of degree n, I write this slightly different than usual. Pn of x I write as the sum from k from 0 to n, and then we have some coefficients ck, but now I write x minus a to the power of k. So we just insert this additional minus a in here, and it's kind of a nice little computation that every polynomial that you write, as we did before, like the sum of from k equal to 0 to n of a k x to the k, has a representation like this as well, and vice versa. So we can also just, kind of use the binomial theorem to really compute these brackets here, so everything inside the parentheses, and to have this against the sum, and then we get a polynomial in x in the usual representation. But this is a standard way of writing a kind of polynomial if we want to emphasize of something which is happening close to this number, to this value a. Okay, and here, of course, c0 to cn are just some fixed complex numbers, just some coefficients. Okay, and we want this to happen. But since this is a polynomial, we have the differentiation rules, and as we've studied earlier in this section, the derivatives of x to the n, the higher derivatives. And by the standard laws of derivatives, we can just write this as the sum of the derivatives of the different summands and so on if we compute the derivatives, which means by the differentiation rules, we get some general formula for the derivatives of this polynomial. And we want this to be true for this, and so we compute this right-hand side now by the standard rules of differentiation. So, by the differentiation rules, we can find a formula for the derivatives, namely the kth derivative of Pn of x, if Pn is given by this expression here. So we've seen that x to the n, the derivative of x to the n, or x to the k, let's say, is k times x to the k minus 1. If we have something inside here, we can apply the chain rule. And by the chain rule, the derivative of this inner expression here inside the parenthesis is just 1. Namely, this derivative is 1, the derivative of this constant thing is 0. So the factor that we additionally get by the chain rule is just 1, so nothing happens. So we can derive this in the same way as we did with x to the power of k, and compute that the kth derivative of Pn is then given as, oh yeah, sorry, let me, no, I'm colliding with notation. Sorry, here's too many k's. Let me call this r, this index. Sorry about that. So this is not related to this case, sorry. So the kth derivative of this is now the sum, and now we have to check. So everything which has exponent here, something smaller than k, will vanish if we derive this k times, because this kind of polynomial of degree r will in this, the r plus first derivative will already vanish, so everything which is below k will vanish in the kth derivative, which means that the sum here starts at k, the rest is 0, and we go to n, and so if we just use the derivation rules that we had before, this is the same as CR times r minus 1, and so on until r minus k plus 1 times x minus a to k minus, r minus k. This is the k-fold derivative of this expression. Now, yeah, and of course this is the case, sorry, for all k smaller than or equal to n, and if we're bigger than n, since this is a polynomial of degree n, this derivative will be 0 for all k bigger than n, as we've seen for the different summands before. Okay, so this is the case here, this is the derivatives. But this means that if we compute the kth derivative of n at the point a, this becomes much simpler. Namely, the kth derivative of Pn in a, if we insert a into this formula, we see that here we have a minus a, so we have 0. So this will be 0, and so everything will be 0 inside the sum, except if the exponent is 0, because then this is something 0 to the power of 0, by definition this is 1. So everything that's non-vanishing is in the case when we have r equal to k, because then we have 0 here. So the only thing that remains here is then ck times, and now we have r to be equal to k, so we have k times k minus 1 times until k minus k plus 1, which is 1. So we go from multiply everything from k to 1, and this is of course k factorial, simply by this computational rule. Yes, this is this times k factorial, and then we get a minus a to the power of 0, which is 1. So nothing else is coming in there. So this is really the complete formula. This is the kth derivative of Pn at a. So this means if we want to have this equation here, so let's call this star. So this equality between the derivatives. So to have star, we need the following. We need that k factorial ck. So this derivative is the same as the kth derivative of f at a. But this gives us an equation for the ck. Namely, this shows us that ck is the same as the kth derivative of f at a divided by k factorial. So this means if we want a polynomial which has this property here for all the derivatives, this is what the coefficients need to look like. So in this representation here, so if we write this up like this in the sum here. So we have really this formula. So this tells us which polynomial we need. This is unique. I mean, if f is given, so we can compute this polynomial. And this means we have our favorite polynomial to do this, and this will be the Taylor polynomial. And I will formally define this again after erasing. Okay, let's define these polynomials formally, motivated by the computation that we just did. Definition for 34. So we have I an interval, f going from I to C, which is n times differentiable, where n is just some natural number, and where we take a point A in the interval. Then the nth Taylor polynomials of f in A is the following polynomial, simply the polynomial we just had. Just to introduce some notation, we call it TNF, TNF of the variable x in the point A. That's a bit awkward notation, but there's kind of no way of really writing them very concise. So this is defined as the sum going from 0 to n, and now we have f to the k in A divided by k factorial, as we just computed, times x minus a to the power of k. Okay. Let's do an example. Let's do some computation, and we can see, even for a very complicated function, that kind of the polynomials of Taylor allow for swift computation. And we take the following example. We take the function going from minus infinity to 0 to r. F of x is simply 1 over x squared, or x to the minus 2, which is kind of the form in which we can derive this easily. So this is obviously not a polynomial, but we can compute the Taylor polynomials of this guy. And this is just to show you once, to get some intuition about this. This is not very interesting in its own, but just to do some explicit computation here. So let's see. This function is obviously differentiable, and the derivative of this is just by the derivation rule for functions of this form. X to the power of something is something times x to, and then subtract 1 from the exponent, so minus 2x to the minus 3, which is minus 2 divided by x to the power of 3. Okay, again, this is differentiable, and f2 of x. So yeah, the second derivative of this, deriving this, means we have minus 2 times, and now we have, yeah, if we derive this x to the minus 3, we get a minus 3 in front, times x to the minus 4, which is 6 over x to the 4. Okay, and so on and so on. And so we can kind of see from this observation that we will just get some x to some exponent, which is always differentiable. And so this is indeed a smooth function. And this, actually, one has to prove this, so I will only write by induction over k and not do the proof. By induction over k, one shows f is smooth, and its kth derivative, there's a general form that you can derive from the scheme that's kind of appearing here. The kth derivative of x is given by minus 1 to the k times k plus 1 factorial divided by x to the k plus 2. Right, we started with 2, and then we get the power is increased then here by 1 in the denominator with each derivative. So we get this formula here, and so it's kind of quite easy to convince yourself of this formula, but technically you have to prove this by induction. Okay, this holds true for all x and k. Okay, now that we have this function, we need a value at which we want to locally approximate this, and I take a to be equal to minus 1. So at this point, we want to approximate this function. So maybe, let me draw the graph of this function here. So this is not connected to this, sorry. So now we're on the left side of the y-axis, if we take a graph like this. And so we, you probably know from high school, this function 1 over x squared. This is a hyperbola, which is now looking like this. Okay, it's kind of approximating the x-axis here, and here it's going toward the y-axis, and going to infinity here and to 0 on the left-hand side. Okay, and assume we're in some position, let's say here, -1. So here we want to approximate this function by polynomials. And now we just have to, this value a to the -1, and now we just have to insert everything we've just computed into the formula to compute the derivatives at this point, insert them into the function, and then we get an explicit polynomial. So we obviously f of -1 is simply 1, and the kth derivative of f at -1, this is -1 to the k times k plus 1 factorial over, and now we have here -1 to the k plus 2. And here we can see that kind of here -1 to the k, this cancels each other out, and all that remains is -1 to the power of 2, which is just 1. So this is just k plus 1 factorial for all k in n. Okay, and if we insert this, we can simply now write down the polynomials. So t1, f of x -1 is so 1 plus, and now we would have the first derivative of -1 at which is 2 factorial divided by 1 factorial times x minus -1, which is +1 to the power of 1. And so, of course, this is here just 2 over 1, so this is 1 plus twice x plus 1, and this is simply 2x plus 3. So this would be the line that we would have here for this function here. Let me, okay, so this would be the tangent line here. This would be the equation, oops, sorry. Of this tangent line, yeah, somewhat like this. So now we approximate this by a quadratic function, so we can just compute the second Taylor polynomial. There we would have t2 f of x minus 1. So the first summons of the polynomial would of course be the same. So again 1 plus 2x plus 1. Now for k equal to 2, we would have the second derivative at -1, which would be 3 factorial. And now inside the Taylor polynomial, we would divide this by 2 factorial, and here we have x plus 1 to the power of 2. So yeah, this is 1 plus 2x plus 2 plus, and here we have 3 factorial divided by 2 factorial is simply 3. And here we get 1 plus x plus 1 squared, and of course this can be computed. So this is 1 plus 2x plus 2 plus 3x squared plus, 2x plus 1. And if we just sort things out, this turns out to be, if we order by degree, this is 3x squared. Here we have 6x, here we have 2x, so it's 8x. And finally 1 plus 2 plus 3, which is 6. So this is the second Taylor polynomial. And this would then be the parabola touching the function at that point, and this would probably be something like this. Well, yeah, it's not really parabola here, but okay. Yeah, something like this. So touching this as a, this parabola here. So we would get the equation of this one. So far, note that we just formally defined this. We haven't proven this approximation property. This will come in a second. But this is kind of how we can compute these. Just for completeness, the general formula here, if we just insert this computation into the polynomial, would be tk f of x at -1 would be the sum k from 0 to n, and we would always have k plus 1 factorial over k factorial, which is simply k plus 1, simply k plus 1, and then x plus 1 to the power of k. So something you can easily compute. Now, the approximation property. There's not that much, so I want to, because it's so nice, I want to have this on the clean blackboard. Let me just erase and then do the Taylor's theorem. We now discussed Taylor's theorem, which really tells us that these Taylor polynomials that I've introduced before are the crucial polynomials to approximate functions by polynomials. Okay, theorem 436. Taylor's theorem, and this is basically one of the two big versions of this theorem that we will see. The other one will follow in the next section. So assume we have an interval. We have a function from I to C, which is n times differentiable in a point A which lies in the interval I. So f is as a whole n minus 1 times differentiable and n times differentiable, so in this point A. Then the function is the same as the Taylor polynomial of f in A, the nth Taylor polynomial, plus some remainder, phi n of x for all x and I. So far there's nothing to show because we can just, so far there's nothing interesting because we can just define var phi n as the difference of these two functions, so this is totally non-interesting, but the crucial part comes now, where this function phi n, so the difference of f and its Taylor polynomial, its nth Taylor polynomial, satisfies a nice equation. The limit of x going to a of phi n of x divided by x minus a to the power of n is 0. Okay, this means that this term here, phi n of x, is going faster to 0 than this polynomial. So faster than the polynomial of degree n. And this really tells us that this is kind of the best approximation of f by a polynomial. I will discuss this a bit more explicit later on. So before I do the proof of this theorem, I do something which is kind of a tool to do this, and I introduce a new category. Namely, before we had theorems, remarks, we have examples, definitions. Now there's something new, a lemma. So what is a lemma? A lemma is basically the same as, it's from its form, it's the same as a theorem, it's a mathematical statement, but lemma is usually some statement that is not that interesting by itself, but that is kind of used to prove something else, or used for a higher purpose, basically. So something which is not really interesting in itself, but is helpful for something else. And so we will now introduce a lemma, some abstract statement which is not that exciting, but which is then important to prove Taylor's theorem. Right? So this is a lemma. Okay, namely, I, an interval. So basically same setting as for Taylor with a bit of additional stuff. We take a point in the interval. We have a function from I to C, which is n times differentiable in A, where n and n. So if we assume that all derivatives vanish in A, so fk, the kth derivative of f in A is 0 for all k between 0 and n. So yeah, the function itself is 0 and the derivatives in the point A. Then we get the following equation. The limit of x going to A of f of the n minus kth derivative of x divided by x minus a to the power of k is 0 for all k between 1 and n. Okay, so let's first focus on this and let's prove this lemma. Okay, we will again prove it by induction. By induction over k. So the base case, this is something we already know if we write this down. Namely, for k equal to 1. So we know that fn minus 1 is differentiable. In A, so since f is n times differentiable, so by theorem 4.6 from above, namely this is some standard form for differentiable functions, we know that fn minus 1, if we consider this as a function and forget for a moment that this is a derivative, this is just some function, in a point x is fn minus 1 in this fixed point a plus the derivative times x minus a. And the derivative here is, of course, fn of a times x minus a plus r of x for all x in I, where the limit of x as x is going to a of r of x divided by x minus a is 0. Okay, this is just a standard thing for a differentiable function. But we know by assumption that this is 0 and this is 0. So this means f of fn minus 1 of x is the same as r of x. So we get limit of x going to a f of n minus 1 of x divided by x minus a is 0, and this is the base case. Okay. So the induction step, this becomes more interesting. So we assume that the limit of x going to a of f n minus k of x divided by x minus a to the power of k is 0 for some k. K is smaller than n, otherwise we wouldn't have space anymore for k plus 1. So assume that this holds. Now we need to consider the k, we need to go to k plus 1. To do some calculus, we let xn to, be a sequence in I with the sequence converging to A. Okay, remember that this limit here exists for all sequences converging to A. This thing converges. So in the notion of sequences. So we know that f is n minus k times differentiable. And now we use one of my favorite tools, namely the mean value theorem. Namely, by the mean value theorem, so now really the standard mean value theorem that we had, namely, if we consider f n minus k, by the mean value theorem there exists some number, blah, blah, blah. I'll fill this in later. Oh, here I haven't erased. Let me continue right here. So we get that f to the n minus k plus 1, so minus k minus 1. This is the thing we need to study. This of xn, this is, since the derivative is vanishing at a, this is the same as fn minus k minus 1 of xn minus fn minus k minus 1 a. And so by the mean value theorem, we know that this divided by xn minus a is the derivative of this function here. And if we just multiply this by denominator, the mean value function takes the form that this is the same as there exists some element psi n, such that this is the derivative of this function here. So fn minus k at psi times xn minus a. For each n in n, there exists some psi n, and now this psi n needs to be between xn and a. And that, of course, I don't know which one of the two is bigger, but there's a nice way to write this where it has to be. Namely, it's either between xn and a, or in the union of a xn. One of the two will always be 0, but yeah, anyway. So there's exists such a psi n with this property. Okay, now let me erase. Let me quickly erase at this point. Okay, so this is the short version for our xn. We have these numbers psi n, which are between xn and a, such that this equality here holds. Now, first of all, since these psi n are always between xn and a, it's an easy thing to see that since the xn converge to A, the psi n converge to A as well. Okay, so much for that. And now we do the following. We want to see that the limit fn minus k minus 1 of xn divided by xn minus a to the power of k plus 1. This limit, we want to show that this is 0. And since the sequence was arbitrary, this is then shows the existence of our limit. Now, if it's something we had before, if we want to show that the term is 0, it's just the same, converges to 0 to show that this goes to 0. This is the same as if we put the absolute values into the numerator and denominator. So this is fn minus k minus 1 of xn to the absolute value divided by xn minus a to the power of k plus 1 to the absolute, so inside here to the absolute value. So now, by inserting these psi n, this is the same as the limit as n goes to infinity of f n minus k minus 1 fn minus k of psi n times, so to the value times xn minus a divided by the absolute value of xn minus a to the k plus 1. And now we can see that we can reduce this fraction by by removing one copy of x1 minus a to the absolute value. So this is the same as the limit of n going to infinity, f n minus k of psi n to the absolute value divided by xn minus a to the power of k. And now this is almost the induction hypothesis, but the problem is that this xn is here. But we've seen that psi n lies between these two, between xn and a. So the difference of xn and a, the xn minus a, this is always bigger than or equal to the difference of psi n and a, right? Because this is just in between. So we make the denominator smaller if we replace xn by psi n, which means that the whole fraction will become bigger. So this is smaller than or equal to the limit of fn minus k of psi n to psi n minus a to the power of k. So like this. But this, by the induction hypothesis, this is the same as, basically the limit as, let's do it like this, psi going to a, f n minus k of psi divided by psi minus a k. Now limit as a function, and to the absolute value pulled outside, and this is 0 by the induction hypothesis. So, since the sequence xn was arbitrary, the claim follows. So the corresponding limit of functions goes to 0 as well. So right, this is smaller than 0, and of course, since this is no negative, this 0 implies that this is 0. This is something I haven't mentioned, sorry. So this implies that this goes to 0, which means that this goes to 0, and so since this is independent of the sequence, we get the claim. Okay. Now, we have proven this lemma, so we now want to use this lemma to prove Taylor's theorem. So proof of theorem 436. And this now becomes very short because this all goes down to this lemma. Namely, put, just to save some notation and to make it a bit clearer, Pn of x is denotes the nth Taylor polynomial of f in A. And we put phi n of x, which is then, phi n, the function that we want to have this limit property. This is, of course, by definition, it has to be the difference of f and Pn. Okay. Now, since f is by assumption n times differentiable, and Pn is a polynomial, is differentiable as well. So phi n is n times differentiable. In A. And we get that phi n to the kth derivative of phi n in A is simply by the derivation rules the same as the difference of the derivatives. So f to the k of A minus the kth derivative of Pn in A. But we've computed that the Taylor polynomials really have this property. This is what was the motivation for the Taylor polynomials, for the definition, that this is 0. So these derivatives are all the same. This is all the same for all k between 0 and n. So, and this means that we're now in a situation where we can apply the lemma. So this is something we've seen above. Maybe add that. Okay, now we have it. Namely, if we now take this lemma, that's not on backward anymore, sorry. But if we insert k equal to n, it really directly follows by lemma 436 in the case k equal to n. This simply gives that the limit of x going to a of phi n of x by x minus a to the power of n is 0. This is explicitly this lemma, and this is what we wanted to show. So this really has this nice vanishing property. Okay, I want to conclude this section with a little remark on the properties, on definitions of these Taylor polynomials. So remark 438. First of all, this version of Taylor's theorem has a name of Taylor's theorem. Is sometimes called the Péano form. Sometimes called its Péano form. Not piano, but Péano. It's an Italian mathematician. It's Péano form. We will see a different one later on, but if you look at different textbooks, the Taylor's theorem might be a little different because there are some versions of this, but this I want to call Taylor's theorem, this theorem we just had. And something I've mentioned before, this property of this remainder function, that the limit of phi n of x over x minus a to the n is equal to 0, this is the crucial one. This means that basically that Tnf of x in A is the best approximation by a polynomial, because by a polynomial of degree n, because the difference is kind of smaller than a polynomial of degree n, or grows faster to 0 than a polynomial of degree n. And this means here that this is the best approximation local approximation of f near A by a polynomial of degree n. So again, I also already told you for the corresponding property of derivatives that they are linear approximations of functions. This is something which is really important. This is the key thing in everything involving Taylor's theorem. We consider this as the best approximation here, and this is what Taylor's theorem does. We will see in some applications how we can use this, but this is the main idea, and this really justifies everything we did before. And this is kind of the idea I told you before. This theorem tells us that these polynomials really have this property that we want them to have. Unfortunately, even the best approximations can be bad. Namely, the best local approximation does not even have to be good. This does not have to be a good approximation. And there's a simple counterexample. Sorry, approximation. There is a simple counterexample that I just want to give you without computation, without checking the details. But I really want you, would like you, if you want to check the details here about this thing. Namely, if we consider the following function, f going from R to R, f of x is defined as, and we have two cases, e to the minus 1 over x squared if x is non-zero, and 0 if x is equal to 0. Now one checks that the graph of this thing looks roughly, I think, something like this, which goes kind of down here very fast and then takes a slight turn and goes back up again. So it just has this kind of kink in the middle. The problem here with this function, or the thing that's so important here, that one checks, and this is something which is non-trivial, and I won't prove this here, but this is something non-obvious. F is indeed smooth with this definition here, and it follows that f, the kth derivative in 0, is always 0. Because roughly the idea is if we apply the chain rule to this function, this basically means we will get back this function e to the something, but multiplied with the derivative of this one, which is some rational function. And then you use the limit behavior of the exponential function, because you do this again and again, and you always have to kind of compare the growth of e to the minus, this is here, if we go to 0 here, we go to minus infinity here, and we've seen that e to the if x goes to minus infinity, e to the x goes faster to 0 than anything polynomial or rational or something. So this is the idea that how you can really prove this, but you can really show that this is always 0 for all k and n. But this, of course, means, just by definition of the Taylor polynomials, that the Taylor polynomial, the nth Taylor polynomial of f, in 0 is always 0, because all the coefficients of the polynomial vanish, because they all involve these derivatives. So this is 0 for all n in n, and this means for the local approximation here is useless. This doesn't help us with anything. The Taylor polynomials all vanish, and they tell us nothing about the behavior of the function, because they are just trivial. So basically these are useless. Okay, and that's the problem with Taylor polynomials. So in theory, you can really approximate functions by Taylor polynomials, but you might just have a function which just doesn't do the trick, with which you cannot do this. But we will see that there are quite some interesting examples where you can indeed use this, and the question is, of course, kind of how good or bad are the Taylor polynomials, and this is something I want to answer in the next section. And in the next section, we will kind of see kind of how we can estimate the difference between the function and the Taylor polynomials, so how to kind of figure out how big the deviation is of a function from the Taylor polynomials. And then we will also see examples, because this is kind of big, massive, heavy machinery here, this theorem, but this of course cries for examples, and we will see some of them in the next section. See you then.